Okay, so now we start lecture 16 with two modules. One is about how actually practically it's possible to measure INL, DNL. You can measure by simulation as well, of course, Monte Carlo simulation before fabrication, but this is actually post-fabrication. And this is one of the basic methods. That's why it's good to learn about the basic methods first. And because this is almost like a static test, therefore the input will be a very low frequency input. Before starting that, I want to give a kind of closure to the discussion in the last lecture, which was related to the positive feedback within a latch or a regenerative circuit in general. See, when you look at a positive feedback system, you have a loop gain, which is the feed-forward gain of A of S multiplied by feedback factor of beta of S. Let's, in general, consider both of them are a function of S. So this makes it very generic case. And closed loop gain, if you have a positive feedback system, so it will be the A of S, 1 minus loop gain. If it is a negative feedback system, it's 1 plus. Of course, this is just the sign of the subtractor at the input. It could be subtractor or it could be a summer, adds. But the notion of positive and negative is just because of that. Otherwise, a negative feedback system can become unstable. And a positive feedback system, if it has a very low loop gain, may be quite stable. Stable. Therefore, stability doesn't have anything to do exactly with the way we discuss, but it is just more with respect to the sign. So now, if you want to talk about the poles of this system, so naturally will be poles of this function, closed loop transfer function. If we were talking about loop gain, so it is only loop gain. Now, notice the poles happen when loop gain is equal to 1. Therefore, if you remove the input and don't get any input or any signal as an input, so you don't have anything called the closed loop gain or closed loop, maybe it would be better overall I call it transfer function. So here eventually in general, it is known as loop gain, but it is because of historical reasons, and usually you have an amplifier amplifying the stage with a feedback factor. But in general, eventually it is the loop transfer function. So similarly here also is the closed loop transfer function. So when we talk about transfer function, that means we have an input and then we have an output. And therefore, ratio of them for a linear feedback system will be the transfer function in S domain. So therefore, as you can see, the poles of the closed loop feedback system will happen when loop gain is equal to. So that's it. Therefore, either you go with the first method and then derive the loop gain in the loop and then naturally without any input. And therefore, here when you go one round in the loop, so you get back to the original point. So therefore, ratio of the two variables should be 1. So therefore, that is equivalent by saying T of S equal to 1, which also is evident from the closed loop transfer function, which will give you the poles of the closed loop transfer function. Fine? So this is just for the clarification. Okay. So, and one thing also, just to conclude, is when you apply an input to get a closed loop transfer function, be very careful that the input that you apply should not change the circuit. That was the second point we discussed last time. Therefore, in the example we had, which was back-to-back transconductors, if you apply a voltage source, effectively when voltage source is 0, you are shorting one of the nodes to ground. That means you are changing the circuit. But if you use a voltage, current source as a source at the input, either of the two nodes in back-to-back transconductors, you are not changing the topology of the circuit when current source is 0, which is this case. Therefore, that's the right way. Therefore, this transfer function in the specific case we were talking about is actually a transimpedance transfer function. So that's it. And it's not exactly transimpedance in generic, it is transimpedance when you have the input current source and output as a voltage at a given node. And because where you inject and where you get the output, if you are at the same point, then it becomes effectively equivalent impedance at that node. If you choose another point, it's fine, then it becomes transimpedance. But both of them will give you same response, which comes from this poles of this transfer function, which is when Ts is equal to 1. So it's quite consistent. Either you follow this method or this method for finding the natural frequencies. Natural frequencies come from the roots of this transfer function, or they are frequencies where you can, at which this T of S will be equal to 1. Okay. Fine. Now we go back to the method of the measurement, and this is from the analog devices data conversion handbook. So what is this method? This method is called histogram method. See, we are not going to have histogram method in this course, but it's very important for you to learn this method from practical point of view. Simulation is more straightforward. In fact, already we have a code, a MATLAB code, where after you simulate an ADC, you take the digital codes for the input, you can actually plot INL, DNL, and we will use that code in the course assignment and project. But that is from simulation when you give the inputs. In fact, from measurement also you can have it and give, but the point is that the input is not from simulation. Input is coming from a real source. And in fact, the input actually is a D2A, can be a D2A. You can have a synthesizer. So therefore, you have a D2A which will generate a signal at the input, and then you will give it to the actual ADC under test. So what is the basic steps of this? So eventually, we want to collect many samples at all codes, eventually all codes, starting from all zeros to all ones. Now here, when we want to say all zeros and all ones, it's not very straightforward to really have equal distribution. Let's say we are talking about an ideal ADC. If you have an ideal ADC and you apply the inputs in such a way that there will be ideally equal number of code for every possible code. So from all zeros to all ones, so we have an input which gets all values of analog in the full scale range, analog voltage or analog current. Correspondingly, we generate codes. So you may have, for example, 1000 occurrence of a single code, and for all codes equally. Ideal case, it will happen that way. If the analog signal is a signal which covers all values with equal numbers. For example, suppose you have an input which is increasing in time and goes from 0 to full scale. This full scale could be voltage or current, doesn't matter. But this is as a function of time. Suppose we have a system which is very accurate and can exactly enable ADC right at this time and can stop it exactly at this time. Say this is time 0 and this is time, say, T1. So now if we give it to an ideal ADC, so for every code starting from all zeros and going to all ones, the number of codes generated for every corresponding word is same, right? So therefore, if you have, for example, m number of all zeros code, it will be same for all. Because input signal is covering all values, and this time T1 is relatively a large value, right? So it's eventually a long time. Okay, it's a long time from T0, from 0 to full scale value. If it is a long time, that means the slope of this rising, for example, linear signal at the input is very low. So eventually it's slowly increases with time. So therefore, all speed related issues will go away. So therefore, it's about the static analysis or static measurement. It's actually measurement, it's not analysis. So it's a measurement. So I agree, all will have same number of occurrences. That means that if you plot histogram of the number of occurrences for each code and plot it, it will be equal columns. The histogram will have equal columns. So therefore, this is the whole idea. If we can control these 2 points very well, initial point and the last point. So this is eventually second bullet item. We have a very slow triangular waveform, and now it becomes triangular. It's not only just ramp, because we may want to repeat this. Suppose if I go only with one round, what would be value of m? 1, exactly. So therefore, I will have one occurrence of all of them. So histogram still will be histogram, but number of samples will be 1. More often, we don't want to do that, because there are always non-idealities in the system. So it would be better to get many more samples of each code. So therefore, we convert this signal into a triangular signal. The only thing is that everything remains same, only we will have also a falling edge. And we can repeat it also. So as you notice, first of all, this is a continuous waveform. We are not interrupting the measurement at any point. So we start from time still 0, but now time t1 will be after some number of cycles. So in fact, t1 now will be here, much more than the t1 that we had there, considering number of cycles. And keep in mind also the slope of this ramp, rising ramp and falling ramp, both is very low. So therefore, it will take reasonably long time as compared to the actual speed of the ADC. So because this is going to be a static measurement. Therefore, this m will be more than 1 depending on the number of cycles. Eventually, for every cycle, you have m equal to 2. Therefore, if you have, say, for example, 1000 cycle multiplied by 2, ideally, you will have 2000 samples of each code. So this is the way we eventually generate the input, and this input now can come from a synthesizer, can come from a very accurate DAC, and because it's low frequency, it is possible to use a very high resolution DAC, which is with a resolution more than even ADC under test, and generate all these codes. Fine. So this is for the ideal ADC, ideal case, all will be equal. Now suppose ADC has INL error. Now what will happen for that? So first we see the setup. So this was the concept, and the block diagram here shows actual setup. So we have some periodic triangular waveform generator. As I told you, it is actually a kind of, could be a very precise DAC. Now question is about this 0 and T1. And question is about the mean value and max value. Because when we start from 0 and we stop at V full scale, so eventually it has to again go back, if you are using DAG, reasonably we can control it very well. And if you have a centralized clock, the way it is shown over here. If you use a waveform generator, which is an instrument, it may not be very straightforward. Therefore, they keep some values below 0 and some values above V full scale, so that to make sure that, everything is covered well. Another reason is that specifically if the switching points are LSV upon 2, for example, starting from input, we need to have values below 0 also, so that otherwise number of samples for the first code will be half. So therefore, because of these conditions, more often actually we are not so worried about all zeros and all ones code, because we know that all zeros and all ones can be separately checked as a single input, just a DC input, for example. And then depending on the shift, we correct for the gain error and offset error, as we discussed before. Therefore, we are not so worried about these two boundary values. We look at other codes in between. So this is the way. So ADCs and ADC under test in this block diagram. And then we have that clock generator, which is the sampling at the frequency of Fs. So we sample the ADC, input is low, but Fs is the sampling frequency, the ADC is supposed to work with it. But input is eventually like a static input for ADC. So it's not very high frequency. High frequency in the sense that it's not reaching to the maximum signal bandwidth. That is, this ADC is supposed to work with. So therefore, we get the samples at the output. And these samples at the output come at different codes. So therefore, we have different codes. Eventually, code increases from all zeros to all ones. Again, code reduces from all ones to all zeros, again increases and so on. So these samples, which are say for example n-bit samples, are coming. So we need to store them, because then after that we would be able to get INL and DNL from these samples, which are stored and they are digital. Therefore, we need a digital memory. However, this is for the cases that the memory, because this is an external memory, so therefore, the memories specifically for non-embedded memories, external memories, the read and write time is not very low, because you have to address, you have to read, you get to activate, enable, and then address the point, the cell, read from cell, latch it, and so on into the say computer. So therefore, eventually if this memory speed is not compatible with ADC speed, you can actually reduce the clock by a factor of k. That means that you are generating many samples, but you are collecting with a lower speed. So that's okay. That only point is that you need to increase number of cycles to collect more samples with the writing speed of Fs upon k. So this will be eventually the whole idea. Now, of course, one thing also we need to understand, if we want to try it with a sinusoidal waveform, because sinusoidal waveform will not give you uniform distribution of codes. Therefore, we need to have an idea about the way that number of points change with respect to time, and that exactly depends on the waveform. Here, because it's a linear constant slope variation with respect to time, so output also will have equal numbers. And that's why we choose the triangular waveform. Therefore, let's assume that the total number of samples collected is m subscript t. Fine. So this is t for total. And then any code that we have belongs eventually from 1 to 2 to the power n minus 2, because we are removing 0 and 2 to the power n minus 1 because of the boundary values. So h of n is the number of hits for every code. That is number of samples that we collect from measurement and stored in the memory. So ideally, if you assume that all samples are latched into the memory at k equal to 1, so, or we can consider m of mt is the number of samples actually collected by the memory, not generated by the ADC. So ideally, we should have this average value of number of hits to be mt upon 2 to the power n minus 2. Remember, we are not counting the first and last. That's why this is only total number of samples for the codes belonging to the range written over here. So therefore, ideally, h of n should be mt upon 2 to the power n minus 2, which is the bullet item 4. But if we have DNL, then actually this h of n now will not be same as before, it will be different. So this actual h of n upon ideal h of n minus 1 actually is DNL of the code, right? So therefore, because depending on how DNL is more than or less than 1 LSB, the number of samples will change. The number of samples for that particular segment will change proportionally, right? So therefore, effectively, you will get the DNL from counting the actual hits, number of hits for a given code compared to the ideal h of n or expected h of n, which is mt upon 2 to the power n minus 2. This is also sometimes called average value, means that on average we expect mt upon 2 to the power n minus 2 uniformly for all of them. But some of them reduce, some of them increase. Fine. So, and we discussed about the frequency, it has to be very low. We mentioned about that, you know, first and last code can be separately tested and then use offset and gain error compensation. And of course, here we assume that ADC is monotonic. As I told you, if we have a non-monotonic ADC, I think we should not even fabricate it. We need to make sure that even after fabrication, if an ADC has become non-monotonic, more often it's not even used. I mean, have you ever seen any commercial product or even research paper which introduces a non-monotonic ADC, unless if it is on purpose? So therefore, assumption here is that really this is a monotonic ADC. Otherwise, the number of codes really are not representative of DNL, because you have codes which are repeated for different values. So eventually some codes are missing and some codes are repeated for values which are not belonging even to that code segment. So therefore, this is not considered here. So this is just an example, and then this plot on the top and plot at the bottom are not correlated. These are just arbitrary plots. So it's just to show the same concept. Eventually on the top you see that the number of hits per code, except all zeros and all ones. You just keep them away from this discussion. It shows even in the analog handbook, they have analog devices handbook, they have shown missing code as well. So therefore, you may have the missing code, but still it will be monotonic ADC. So with that condition, you see that. So eventually you see number of hits on average or ideally is supposed to be MT, which is the number of recorded codes. Total number of recorded codes in the memory divided by 2 to the power n minus 2. But some of this high number of hits or samples per code are more than the actually expected value. Some of them are below that. So that is exactly correlated to the DNL. Because if DNL is 0, that means all of them will have equal height eventually in this histogram. So, but if it is not, depending on whether we have the positive DNL or negative DNL, so the number will increase or reduce. Eventually, if you have positive DNL for some segments, so you will have more hits. And if you have the negative DNL, that means it has been shrunk below 1 LSB, so therefore number will reduce. So therefore, these are like, this is something you can get from simulation and this is what you get from measurement, but you can actually convert them based on the expression that is given over here. And when you have the DNL, then you can derive the INL from DNL. So INL is eventually integration of DNL in discrete domain. We are talking about discrete domain, codes are discrete, so it becomes summation. So effectively, that generation of INL from DNL also is a simple sigma MATLAB code. So therefore, this is the way you can, in a basic way, you can measure INL and DNL for a fabricated ADC or the real ADC under test. So you can have the same thing for simulation, but simulation even can be, simulation also is similar, but in simulation you don't have any memory per se, you eventually store them. It's software only. There's no external memory. That's why K is equal to 1 for simulation. Otherwise, for simulation also, you can give the same periodic triangular waveform to the ADC. And now this ADC from simulation is not an ideal ADC. It is a post-Layard extracted ADC with Monte Carlo. So that means that random variations will be included, also corners. Okay, so therefore overall we have the method, and this method is a very slow method. And the overall measurement time depends on the number of bits, depends on the factor K if it is not 1, depends on the sampling frequency, and depends on the average number of samples per code, that S, which is shown by letter S here. Average number of samples per code that we want. If you want, say, 2K samples per code, or if you want, for example, 1K sample per code, so multiply by n number of bits will define the number of samples we need. So this eventually is a slow measurement, but that's okay because this is the measurement time, which is not still too high as well. So this is eventually the only main requirement, and of course memory should have the enough size for storing eventually 2 to the power n, of course minus 2, because two codes are not there, so therefore it's 2 to the power n minus 2. So codes, and S is the average number of samples per code, and then we have the sampling clock period, and then K is the factor by which we reduce the frequency so that we would be able to store in them. Okay, so in fact, if you give, say, sine wave, see, first of all, you don't need sine wave. See, you need sine wave when you are operating at the frequency of that maximum frequency of the input, and that is not really directly applicable here, though you can use it, but everything now has to match that frequency. But suppose if you have a sine wave, let's make it exactly compatible with this triangle. Sine wave, if you want to cover one cycle, this is half cycle. I can make it half cycle, but let's make it full cycle. So therefore, effectively, it will go this way. Now, you know, when we have the maximum slope, we will have minimum number of codes. And where we have the minimum slope, we will have the maximum. Now, what will happen is that, therefore, the distribution will not be uniform. That means, if we plot histogram as a function of code, say this is all ones, and this is all zeros. So, and then say, for example, this corresponds to 0 and all zeros. And this corresponds to all ones. So for the codes which are close to all zeros or close to all ones, we will have high number of hits. Something like that. And then for the codes which are at the middle, like for example, half 0, half 1, we will have the minimum number of hits. Say something like that. So we get this kind of distribution. So that means that codes will be very high occurrences. Then it will start reducing here. Then again it starts increasing, and then again reducing. So therefore, it is like that. It is following a kind of shifted sine wave. So therefore, we know already what waveform we have. And now we have a new distribution. Now therefore, when we want to get the INL, DNL, we need actually, instead of considering its uniform, consider this one and get the distortion or eventually deviation from that. Because that means now ideal heat, we know ideal heat still between for every code, ideal heat with sine wave input. We know the measured values, therefore for every heat, considering say 0 is correct. So for every heat we can still calculate one by one based on the number of hits, but it will not be uniform, it will be this way. So still, you know, suppose the number of hits here should be M1 and number of hits here should be M2. And so suppose this is M1 and this is correct. Say for example, the first one say M1 and the next one is M2. So M1 is correct. So therefore for M2, it is still difference of M2 minus M1. It's not actually difference. So it is eventually, yeah, it is M2 from measurement, M2 from eventually expected M2 minus 1. So if these two are equal, so ratio will be 1, NL will be 0. Otherwise, exactly the portion, the proportional to the reduction or increase in the number of samples for M2, equally the segment size has increased or reduced. That's why still is applicable. The only point is that it's not same for all codes. Yeah.
So the expression is applicable still.
Expression is applicable, but actual numbers are not applicable.
So ideal value changes for the expression.
Yeah, because it is ratios. For DNL, it will be same, and then INL anyway is measured, is estimated, is derived from DNL. Yeah. So actually, it's correct. So that means that this is not distortion. This is because of the waveform, but the ratio of change in the number of samples for every code still is representative of the segment. Because actually, you know, that I have to, in fact, slightly correct what I said. See, if you have LSP distance between two code transition points in the ADC characteristics, so say this is fixed, and this has increased by some factor, independent of what is the waveform. So therefore, this is the one, and this is the new one. So if this has increased, it is equivalent by saying that LSP or distance has increased to say some factor. Say for example, this is 1.2 LSP. Something like that. So therefore, as we increase this height, that means we are increasing this width proportion. Yes, yes. M2 is, for example, for code 2, M1 for code 1, and so on. So then now we can move to the next module, which is exactly the extreme point with respect to flash ADC, and that is successive approximation register ADC, which is called SAR ADC. And our first reference, main reference will be, but I will give more eventually analysis and information around that, will be from Razavi's another article. This article has two ADCs, pipelined and SAR. So we will have both of them. So he starts with pipeline and then moves to SAR ADC. I think we should make it reverse. So therefore, I make it reverse so that then I will move from SAR to pipeline, because these are two extreme cases, and it will be good to have first these two extreme cases. Flash ADC already we know is one extreme, and SAR ADC is the other extreme. So what I mean from extreme now we will see. Actually, extreme is defined in the first two lines. In flash ADC, all bits are generated simultaneously. Therefore, flash ADC is the fastest ADC, right? In SAR ADC, it is exactly opposite. So one bit at a time. That means 1 bit, say, per clock cycle. Therefore, SAR architecture is the slowest architecture. So we go from the fastest to the slowest. So of course, it is clear that when we move from fastest to slowest, we gain something, we lose something. See, for example, SAR ADC is very sensitive to clash ADC, clock jitter at high speed applications. SAR ADC is slow. So therefore, naturally, it is not used for very wide band signals. Say if we don't have, say, gigasample SAR ADC, practically, they are all limited to hundreds of megahertz or megasample per second as of now with today's technology in CMOS. Of course, if you go to gallium arsenide, that's a different domain. So there you can actually have faster speed because mobility is very high compared to silicon. So therefore, but how does SAR ADC works? Generating 1 bit at a time. Actually, it follows a binary search algorithm. And you need to sample and hold the signal. So therefore, we have a track and hold circuit anyway. But it can be embedded within the ADC that we will see. But it uses a binary search algorithm. That means that first, it divides the code into 2 parts. And then we'll see whether the input is the below the first, the middle value of the codes, below that or above that correspondingly. So eventually, it divides the full scale into half. So this is a kind of binary search. So it divides it into half. So we full scale upon 2. Then it will check whether the input is above V full scale upon 2 or below. If input is below V full scale upon 2, then it will check whether it is below V full scale upon 4 or above V full scale upon 2. If it is above V full scale upon 2, then it will check whether it is below 3V full scale upon 4 or above that. And it will continue that way. Of course, it could also start from the shifted version. You know that LSP upon 2 shift. Therefore, still it is a binary search, but you can shift all these values by LSP upon 2 down. So method will remain same. Eventually, it tries to divide the range into 2, upper half, lower half. Depending on that, again the next half will be divided by 2, and this will continue till number of bits are generated. So therefore, every search and generation of the reference value becomes at least 1 clock cycle, at least. Therefore, you need for n bit, you need at least n clock cycles. Exactly opposite to SAR ADC, flash ADC. What is the advantage? Then you need only 1 comparator because it's cycle by cycle comparison. You don't have simultaneous comparison. Therefore, all those issues of too many comparators, which was limiting the number of bits in the ADC, flash ADC, goes away. You have only 1 comparator. That's the advantage. And because you have 1 comparator, offset of that comparator eventually results in the shift, offset error, not really distortion. That's another advantage. But SAR ADC needs to generate reference levels, just like flash ADC. But we need to generate 1 reference at a time. Therefore, we don't need really to have the static power dissipation. We just need to generate reference at a time. So once we have 1 clock cycle, we full scale upon 2, 1 clock cycle, we full scale upon 4, and it need not be constant, it changes every cycle. Therefore, it need not be static. Therefore, it is possible to even remove the static power dissipation completely from the reference generator. And therefore, because comparator also can be a clocked comparator the way you see in the picture, so therefore you can have almost like a static power consumption close to 0. Therefore, what are we losing? Time, speed. What are we gaining? Energy and accuracy. So therefore, we can have more number of bits, more resolution with SAR ADC as compared to flash ADC. With the calibration techniques post fabrication, these days even above 10 bit SAR ADCs are reported, while you can't find 10-bit flash ADC. But at the same time, speed needs to be compromised, but it depends on technology as well. But anyway, there is a limit for a given technology. Do you remember we had eventually the limit on the speed of the charging a capacitor using a switch. So eventually everything was limited to the length of the switch and mobility. So we cannot really go below some value with respect to length, and we cannot go above some value with respect to mobility. So it's the technology dependent. So therefore, for a given technology, there is a limit, but therefore we have a limit on the speed, but we can manage the resolution, which is much better than flash ADC. Okay, so this is now the whole block diagram on the right. So there is a track and hold circuit. There is one single clock comparator. And to generate all these reference levels, we can actually use a very precise DAC. Therefore, we can have a DAC which has the same required accuracy of this ADC, generate that DAC, or use that DAC to generate reference levels. And this DAC could have zero static power consumption. So therefore, because we are changing it every cycle, we are changing the reference by a factor 2. So it is like you just change the code at the input of the DAC, you will generate a new reference value. Fine? So the concept is clear? Yeah? Okay. So here, just to show one diagram. So the green color, so I have drawn two V-in values, two arbitrary cases. Just see, this is like a 5-bit ADC. And it eventually creates this kind of tree. It's like a tree diagram. It's really binary tree. So every time you move from left to right, or eventually ADC moves from left to right for the comparison purpose and generates bit by bit. So eventually, how does it work? Let's say we have the y-axis as full scale range. And then say right now we are talking about V full scale upon 2 rather than V full scale upon 2 minus LSB upon 2. But as I told you, you can just shift all of them down. So therefore, say first reference level is 16 LSB. So this is generated by DAC. That means first it is generated by DAC, and this first eventually comparison, which is happening at the input of the comparator, compares the held input with 16 LSB. Now suppose in this case, let's say we are talking about V in 1, which is shown by green color. So input is below that. Therefore, we know that the first bit is 0 because input is below. So therefore, the first bit becomes 0. Then we move to the next reference level, because now we want to know whether it is in the upper half between 8 and 16 or lower half between 8 and 0. So therefore, the next reference level will be 8, which is generated by DAC. So eventually DAC first generates 16 LSB, then DAC generates 8 LSB. And then because input is input again is below 8, therefore the next bit also will be 0. So therefore, the first 2 bits from left, like MSB, and the bit after MSB, now are 0. Then we will move to V full scale upon 4. And then again input is compared. And now you see input is above. So the output of the DAC now is 4 LSB. And the input is above 4 LSB. So therefore, the next bit will be 1. So now we had 4 LSB and 8 LSB. So we need now to compare with 6 LSB. So again, input is above 6 LSB. So therefore, the next bit is 1. And next level is not compared with anything else, means there is no other level. So the last level, anyway, input is above the last level, which is eventually 7 LSB. So the last bit also will be 1. So therefore, now code is generated eventually. So therefore, we have eventually 5. Let's say each process takes 1 clock cycle. So we have 5 clock cycles. And for VN2 also I have written the code is similar. In fact, VN2 and VN1 only have difference in one LSB. So therefore, the code for VN2, which is slightly below 7 LSB, will be 0. Okay. So now here is one thing which is very important is this comparator should have resolution which is required by this ADC. That means this kind of resolution. This is one. Second thing, DAG also should be better than this ADC, so that these reference levels which are produced themselves should be better than LSB of this target ADC error. So therefore, if suppose this is for 5 bits, it will be good to have a DAG with 6-bit accuracy. That will give us, or 6-bit resolution, that will give us eventually the right operation. Otherwise, if the output of the DAG has a 4-bit resolution, this will not give you 5-bit resolution. Comparator also should be able to resolve with a resolution better than half LSB. So these are the requirements on the comparator. That's why it is very important to also consider the noise of the comparator here, specifically when number of bits are increasing. Another point here is that because reference levels are produced dynamically, it is not like a flash ADC where they are static. Of course, in flash also we had the problem because of the kickback noise and because of the settling time. And naturally, there should be a settling time associated with reference levels because of the parasitic capacitors. But here, actually, they are completely produced dynamically. There is a DAG. Therefore, settling time of the DAG should be fast enough if we want to resolve everything in one clock cycle. Otherwise, if the settling time of the DAG is high, then actually it will get, say, for example, 5 multiplied by 2 clock cycles, 10 clock cycles. Specifically, we have also a logic circuit here because the logic circuit is responsible to control the speeds, generate the code for the DAG, depending on the output of the comparator. So for example, here, when output of the comparator was 0, so therefore it had to make the first bit 0, latch it in the register, then it had to give the next code for the DAG to be Vref upon 3 Vref upon 4. So Vref upon 4 rather than 3 Vref upon 4. So therefore, delay of this logic circuit also is part of the delay of the whole cycle. So therefore, one is tracking, which is okay. So track and hold anyway has its own design and delay. But other than that, we have the delay of comparator, delay of the register, delay of DAG. So these 3 eventually will add to the delay of the whole loop or one cycle of conversion for 1 bit. And that's why SAR ADC suffers from this delay. But it can be much more accurate compared to flash ADC. Okay, so this is with respect to speed. Now, how to implement this DAG without dissipating any power dissipation? So actually, one of the very well-known DAGs which avoids power dissipation is capacitive DAG instead of resistive DAG. Therefore, here today also, we also learn a DAG along with ADC. And this DAG is called a capacitive DAG. So you see there are capacitors which are binary weighted, C, 2C, 4C, 8C, and one additional C. Because if you add them together, for example, in this case, 8 plus 4, 12, plus 2, 14, plus 2, 16. So that means that for a 4-bit ADC, eventually you have the full range, 16. This is important for generating the reference level because we need Vref upon 2, Vref upon 4. We need binary division. This binary division is achievable using these capacitors. We need a reference level because we are creating divisions of the Vref using capacitive division. So eventually, this DAG does the capacitive division of Vref for you. And that will generate reference levels dynamically. That's why this network of capacitors has to settle before comparator take a decision. Okay, and this is more often a clocked comparator because input of the comparator has to settle and then we have to activate the comparator. Okay, and then there is a common mode level, because in CMOS technology, we can't have here 0. This is what you see in difference. In Razavi's article, he has used generic input of 0, but this is actually a common mode level. So VCM. And then we have the input. Input is fixed. Input eventually has to be used for all cycles of conversion. Therefore, we can actually store input on this capacitor. Instead of putting a separate capacitor of track and hold, we can use same capacitors and so store input on all of them. So therefore, eventually the whole idea is, if you have a comparator and we want to compare V in, which is stored on a capacitor, fixed, with some series of Vref I values, and Vref I is generated by a capacitive DAC. Instead of that, what we can do, similar to what we had for differential flash ADC. So we use this technique, that technique over here as well. So we can have here VCM, and here we can have a block, which is that capacitive DAC. But this capacitive DAC, eventually, we apply V in as a bias and VCM. And we apply the n-bit code as a digital input. Now what will happen at the output? You will have V in, you will have VCM plus Vref I minus V. And V in itself has a common mode. Eventually V in is equal to VCM plus small signal, which is the actual signal information. So therefore, this 2 VCM will go away. Eventually, you will have the comparison. So this will be, and Vref also will have its own common mode. So therefore, effectively, we will have VCM plus eventually Vref minus a small signal V. What does that mean? We are comparing Vref minus V in with 0. So therefore, instead of giving input from a separate track and hold, we use V in. So VCM, you can ignore VCM, do small signal analysis. Differential mode analysis of ADC, how it is different from anything else? We just make this VCM 0, right? And everything else can be differential. Of course, here, real differential, we don't have, input is single-ended, but comparator at least is a differential element at the input. It has differential input. At the output is single-ended. But therefore, here you can just make for small signal, this can be 0. Even forget about differential single-ended. We are just talking about the large signal and small signal. So you make the VCM 0, you have a small signal. That's it. And in the other case, when differential mode and common mode in differential architectures, when you use differential mode, naturally it is like a small signal. Anyway, so this is actually the concept. The concept is that, first of all, why do we need to have a separate V in, separate Vref? We put them all in one capacitive DAC. However, capacitive DAC plays 2 roles. For V in, it is like a track and hold circuit. For the digital input, it is like a DAC. So therefore, digital code will be converted to the corresponding reference values. Why Vin will be like a bias, like VCM. So stored on the all capacitors and constant over all number of conversion cycles. So suppose if we have n bits here, say for example 4 bits, so 4 cycles, Vin remains constant, and we don't. It's a hold mode eventually. So now on the right side, what I am doing is I'm showing the entire circuit just for the sake of comparison to have it. But on the left side, we start from the samples eventually, phases, one by one. First phase, of course, is the sampling. That's why I'm showing the track phase at the beginning. Okay, with this example, I have used now, even I have removed this 8C just to make it simple, 3 bits for simplicity. Okay, so we have this binary weighted capacitors. The first thing we do is that we charge or bias all these capacitors with VCM minus Vin. What we have here, VCM minus Vin, right? That's the constant part. So therefore, we charge all capacitors with VCM minus Vin. And this symbol I have used here, thick line, is eventually closed switch. These are closed switches. Fine. So now we have biased everything. Sure. Now we want to see that how to use it. And I show also a hold phase, just something like that, a quick hold phase. Suppose if you opened all these switches, so you have eventually now you see VCM minus Vin on these capacitors, and nothing will change because these capacitors, we assume the parasitic capacitance at the input of the comparator is negligible, so therefore charge remains on these capacitors as it is. I mean, eventually right now, I don't talk about the charge sharing and clock feed through. Let's assume all taken care by this proper design of switches and proper sequence of turning on and off. That we will discuss later. Let's first learn about the operation. So therefore, we have 4 switches over here connected to the bottom plate of capacitors, and 1 switch horizontal which has the job of eventually connecting the top plate to VCM to make sure that these capacitors are charged with VCM. Okay, so these are also shown on the right side in general. So eventually the capacitors right now we are talking about, switches, are these switches S21, S11, S01. So eventually bit 2, bit 1, bit 0, 1 switches, these switches. And there is also a switch S-in for this additional capacitor, which is also connected to V-in. Bottom plate is connected to V. So therefore, we are talking about these 4 switches as of now. And there is a switch common mode, which is here, closed. Fine. In hold phase, now all of them are open. Now we want to generate eventually reference levels. Now actually the DAC operation starts. DAC operation eventually is taken care by connecting the bottom plate either to ground or VREF. That is the way we generate that capacitive division. And because all capacitors are charged by VCM minus Vin, that doesn't change with this switching because top plate is open. Therefore, nothing will change as far as the bias is concerned. Only VREF fractions will change. So let's say first comparison phase. The first comparison phase is comparison of VREF upon 2 minus Vin with 0, right? So that is what we want to generate. Minus Vin is already generated with CM minus Vin. So that's not the point. Here we want to generate actually VREF upon 2 added to the VCM minus Vin. So what is VREF upon 2? That means that you should have the capacitive division when 4C is connected to VREF and 4C is connected to ground, right? So that is exactly the point. That means the first capacitor, which was like an MSP capacitor, will be connected to VREF through S22, which is shown over here. Rest of them are connected to ground through this ground connected switches. Now there will be a difference. See, top plate, as you can see, is open. It's not connected anywhere. And that is exactly the situation we had in differential track and hole at the input of flash ADC when we were storing eventually Vin. So it's the same thing, V in, of course, and V common mode. So it's the same thing. We want to see what would be here at the input of the comparator. There also was the same thing, input of comparator. So here, for the biasing, it was V in. Now it has changed to Vref. So how much delta V we have here? Vref minus V in. This bottom plates, 3 bottom plates of capacitors 2C, C, and C. C is the unit capacitor. And actually in the layout also unit capacitor will be used. I will show you also layout of these capacitors. It's very important in matching. So we have to have exactly these binary ratios. So other inputs are actually going from V in to 0, right? So it was V in, it went to 0. For the first input, for the first bottom top plate, the reference level is generated. So therefore, if you look at the capacitive DAC, you have the delta V of V in, Vref minus V in at the bottom plate of 4C, and you have V into 0 delta V at the bottom plate of other capacitor. Together they become 4C. So therefore, what would be VA? VA will be, because it's a linear circuit, just make a superposition. So common mode is the voltage which was already there, so we are not changing it. But now the difference at the input, or delta V, has become Vref minus V in. So it will be upon 2 division. Then for this input, this is superposition. Again, same thing. You make the left 0, and for this input, it will be 1 upon 2. New value 0, initial value V in. So delta V here is minus V in. Delta V here is Vref minus V in. So therefore, VA becomes V common mode plus 1 upon 2 Vref minus V. So eventually, we are not changing anything. All we are changing is this component of Vref. 1 upon 2 Vref, 1 upon 2, 0. This V in has not changed. See, it is still there. So therefore, because here you divide by 2, again you get it. But 1 upon 2 Vref, because there was no Vref before. That's why 1 upon 2 Vref now is established. It's added to V in. Okay, and minus V in will remain same as before. Fine? We expect also, because we had this VCM minus V in on all capacitors, so we don't expect that to change. So therefore, now we have the first step, and this input is established now at the input of comparator. After it settles, of course, this is a steady state value. After this capacitor settle to their value, because they have the switching from V into 0, V into Vref. So then we will be able to have the output of the comparator, which says whether V in is more than or less than Vref, according to this input. And accordingly, the decision will be made. So now here we have to consider 2 cases. One is the case V in is more than Vref upon 2, and one is the case V in is less. Therefore, for the second comparison phase, I consider case 1 and case 2. So let's assume that V in is more than 1 upon 2 Vref. Okay. If V in is more than 1 upon 2 Vref, that means we have to compare it by 3 upon 4 Vref, right? So therefore, that means we have to add 1 upon 4 Vref to this circuit. So to add 1 upon 4, that means that we don't need to change this because it's already more than 1 upon 2 Vref, so we have to keep that. But now we add 1 more Vref to the capacitor 2C. So eventually bottom plate of 2C now will raise from 0 to Vref. That means that now we have capacitive division of 1 upon 4, which will give us Vref upon 4. So Vref upon 4 now will be added to the voltage at node A. Therefore, voltage at node A is what we had at the beginning plus the new value Vref upon 4. Therefore, the actual input of the comparator now is 3 upon 4 Vref minus V. That means if V in is more than Vref upon 2, what we are doing, we are adding a Vref upon 4. And if input is less than Vref upon 4, we have to actually go to the second half and then remove Vref upon 2. So that is what we do in the next slide. So therefore, you see, therefore, now 1 bit is already established because we know now V in is more than 1 upon 2 Vref according to the previous comparison, output of the comparator. So 1 remains, the other 2 bits still have to be resolved. Fine? The same thing will continue. Now, in the second comparison phase, if we have the case that Vin is less than 1 upon 2 Vref, the first thing which will happen is the logic circuit will make the first bit 0 because we made it 1 to generate Vref upon 2. But then now because input is less than Vref upon 2, the logic circuit will make it 0. That means we make an assumption, but that assumption was not correct. Fine, therefore that means now we have to take the bottom plate of 4C to ground and generate now Vref upon 4. So therefore the bottom plate of 4C goes to 0, bottom plate of 2C will go to Vref. So therefore now what we have is eventually this part now will go away from what we had. That means that we are deducting minus Vref upon 2 and we are adding Vref upon 4. So therefore this previous term which was Vref upon 2 now is removed and the new term only is Vref upon 4. In the case 1, this was there, Vref upon 2, and we added Vref upon 4. Now we remove it and then we just keep Vref upon 4. So therefore the input of the comparator now becomes simply VCM plus Vin minus Vref upon 4. So therefore Vref upon 4 remains only. Okay, this is for shifting. So eventually now we get the next bit, right? And then again we will continue with the next bit again, whether it is, if it is more than Vref upon 4, then we have to generate 3 Vref upon 8 and so on. So this is exactly based on that diagram, tree diagram. So one thing also, if you notice, actually what is this loop? This is like a negative feedback loop which eventually goes through different cycles and finally settles to the minimum error because comparator is a high gain element, right? So there, and you have a negative feedback loop. So therefore, over number of cycles of the comparison, the difference between the analog signal and the input of the comparator will settle at a value which is closest possible value because DAC, output of the DAC is quantized, it's not continuous. So we have a limit on the minimum error which can be absolute minimum error which can be established here. And that will be determined by the resolution that we have in the DAC, right? The resolution of DAC will determine. So eventually that will be limited to the resolution of the DAC. But you can see very nicely that if this is Vin 1, that's, for example, the first initial assumption. So therefore, the difference is the error. And this error is reducing to this value. And it converges. So I told you about shifting. So therefore, in case you want to shift, that is also possible. So for example, here, suppose if I want to shift by Vref upon 16, half LSB. So eventually means that Vref upon 2 has to be shifted by Vref upon 16. So there are ways to do that. And this is one way. Eventually, for example, this is the case that we have the code 011. So eventually you are adding one more Vref over here so that you are reducing eventually the code by the last bit, which is Vref upon 16, by LSB, half of LSB. So there are ways also to make it simpler with a different value of resistors, see capacitors, for example, here. So instead of Vref upon 2, I want to generate 7 Vref upon 16. So I can actually generate it by using non-binary capacitors. But the only problem is that these are not binary weighted, but this is one way as well. You can. So these are like, here you are generating, instead of 3 Vref upon 4, you are generating 11 Vref upon 16. So that means that you can actually do the shifting by changing the way you size the capacitors or the way you actually switch them, specifically sizing. One thing they actually do is that if you have very large number of, it is very common when you have very large number of bits. So you have too many capacitors. So imagine that this is like for 3 bits. But if you have, say, for example, 10 bits, now imagine that you are going all the way to 10 to the power 2 to the power See, this is for 3 bits, it is 2 to the power 2, right? You add them all together, actually you will get 2 to the power NC. Do you remember we had similar thing in the flash ADC? So which was resistive ladder was 2 to the power C unit, R unit, here are C unit. So if n increases, so you have eventually power of 2 increase in the area. Area of the capacitor, capacitive DAC in SAR ADC is huge, and that's one of the problems. However, there are ways. For example, what they do is that instead of using binary division all the way, they use different ways, that the way I showed you right now in the last slide, to actually reduce size of the capacitors to generate the levels. So this I will show you some of the techniques that they use to avoid this large size of the capacitors in the SAR ADCs. Okay.